Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. Over the last several videos, we've established the problem measurement error in X causes attenuation bias. OLS underestimates the true effect because part of the variation in X is actually just noise. So obviously the next question is, can we fix this? The answer is yes, and surprisingly, you've actually learned this method before, but you've used it for something else. And it's indeed the instrumental variable. Now, this connection surprises most students. If you remember, IV was introduced with a mini arc by itself to solve endogeneity from reverse causality and also omitted variables. But measurement error creates endogeneity too, though from a different channel, and the mechanism ultimately is the same. So in order to go through that, let's recall why OLS fails. And if you remember, we had the true model looked as y equals to beta 0 plus beta 1 x star plus u. So this would have been the true model. However, we observe x equal to x star plus some noise v, okay? So what happens is that the OLS doesn't see the actual x star, it only sees x as a noisy version of the truth. So the variation in x in here contains two components. It contains the true signal, meaning the variation in x star that genuinely relates to the y, and noise, meaning the variation in the v here that has nothing to do with the y. And OLS cannot separate them, so it uses both of them and ultimately gets a biased estimate. So now notice something important. Measurement error creates the same formal problem as OVB, omitted variable bias, and reverse causality, which is the expression that you've seen consistently throughout most of the videos in this series, covariance of x and u being now different from 0. So the violation of one of the Gauss-Markov assumptions. Now, the source here is different, right? Because it's measurement error, not an omitted variable or reverse causality. But the consequence is identical. So the explanatory variable x is correlated with the error term u. So x is endogenous. So why does the covariance between x and u is different from 0 here? Because keep in mind, you had x as x star plus the v. And OLS uses this x instead of the x star. So the true error term now becomes u minus beta 1 v. And v here is part of x, so x and the effective error are actually correlated. So same violation, just different origin. So keep in mind, what is happening is that you've got omitted variable bias, which has covariance of x and u different from 0, which gives you endogeneity as a problem. You have reverse causality, exactly the same issue, and you've got now measurement error, which gives you exactly the same thing. So they all end up in endogeneity. Okay. So three very different problems in the real world, one common mathematical consequence, meaning the covariance of x and u is different from 0. And ultimately, there will be one common solution. and that is the instrument variable. So suppose that Z is a variable that is correlated with the true variable X star, okay, is uncorrelated with measurement error V and is uncorrelated with the structural error U. Okay, so look very carefully what we've actually done by coming up with all of this setup. We're saying that we're looking for relevance. We're saying that we're looking for exogeneity. Okay, so ultimately, if I were to draw this in a graph, what I'm saying is that I have this Z who is affecting my X, who then X star, who is then affecting my Y. Okay, and this has something to do with the observed X, which is X star plus V, okay? So the instrument is related to the true regressor X star, not to the noise V here that contains our measurement error, okay? So this is the key. Z can see through the noise to the true signal. And this is just slightly different from the OVP case, because here the exclusion restriction requires Z to be both uncorrelated with the measurement error V on top of the U. So these two come together and both conditions must hold. Now, why does IV work in the case of measurement error? So remember what IV does. It isolates the variation in X that comes from the instrument. The variation reflects exactly how the Z moves X star, the true variable, and it does not reflect the measurement error V, because Z, as we said, is uncorrelated with the measurement error V, okay? So IV acts as a filter. It extracts the clean, genuine variation in X star and discards the noise. Now, the second stage uses only that clean variation to estimate beta 1. So results should be no attenuation bias. Formally, in this case, remember, we have had that the beta hat IV is the covariance of Z and Y divided by the covariance of Z and X. Now, since Z is uncorrelated with the V, you're going to have that the covariance between Z and X is actually just the covariance between Z and X star, okay? So the instrument ultimately only picks the true variation, and the attenuation factor disappears, because normally you would have had here also the covariance of Z with the V, but clearly this is going to be 0. As a concrete example, imagine that we've got education, which is self-reported. And some people round it up, some people round it down, some misremember. OLS uses this noisy education variable and basically gets the attenuated estimate. If we were to introduce the instrument distance to nearest university, now distance influences true educational attainment, basically how many years someone actually studies, but distance does not determine whether someone accidentally reports 15 years instead of 14. So distance is uncorrelated with the measurement error. So IV, again, isolates the variation in education that distance creates, which is variation in true education, not in the noise. There is a caveat, however. So it will only work if instrument is valid. So clearly all of these three conditions that I've mentioned in here need to be satisfied, which is exactly the same condition that we studied in the IV arc. So the fix works, but it requires a good instrument. And clearly finding an instrument that is uncorrelated with measurement error as well as the structural error is now a stronger requirement than what we saw with reverse causality. So this has to be, if you're doing a work on measurement error, this is worth being explicit about in any applied work. Okay. So in a sense, this is also the moment everything connects together. You've got instrumental variables not being designed to solve just one specific problem. They were designed to solve all of the problems that we mentioned right here. So we've got an omitted variable that contaminates X, reverse causality that creates a feedback loop, measurement error that adds noise to X. And the IV solution is always the same. Find a variable Z that moves the true X through a clean channel and only use that variation to estimate the causal effect. So one tool, three problems, same logic. While IV is a powerful solution, keep in mind it requires finding a valid instrument, which is not always possible. In the next video, we'll explore other approaches that researchers use when a good instrument is not available. So stay tuned, and I'll see you then.